Hello, my name is Yongtai. It's my privilege to present my summer research conducted with Swornim and Dr. Daniel Salinas-Duron. Our research is named Detection of Pelicans at Great Salt Lake using faster RCNN. Now let's begin. Over the breeding season, Gunnison Island at Great Salt Lake is filled with pelicans. Human activity has played a role in decreasing the number of pelican population in Gunnison Island every year. Population tracking of wildlife can be done non-invasively using remote cameras that's more efficient than human effort. A lot of such images has been collected. Pelicans in those images are both difficult and time-consuming to count manually. Convolutional neural network are the state-of-art solutions for the problem of object detection in the image. We trained a convolutional neural network to help count the number of pelicans from image. We code our program in Python using PyTorch package and its subpackages.
Right, so I'm going to talk about why convolution network is good for image processing. So convolution networks can process multidimensional data. So image is a 2D data, right? So convolution net is going to be a good, good neural network to process image because of that. And the other thing is that they're trained using the same well-known algorithm called backward propagation. So what that means is that we can implement the same techniques and knowledge that we have in a non-convolution neural network in convolution neural network as well. So over the years, convolution neural network has seen a lot of development. So RCNN introduced CNN, convolution neural nets, as object detection, and then later on we have fast RCNN, and then with better proficiency and speed. So for this purpose of our research, we implemented ours on faster RCNN architecture. So in our architecture, it mainly has 3 parts. So the first one is called region proposal. So it's the green one right here, if you can see the picture. So what the region proposal does is that it proposes like regions where there might be an object. So the small green boxes right here are the place where our region proposal has said like, oh, there might be some image like objects there. So for that one, we use a pre-trained feature pyramid network. And the next part we have is feature extractor. So what feature extractor does is that it detects different features from images like edges and contrast, those kind of features, and then it passes it through the region proposal network. So for this one, we used a pre-train as well, and we based it on a ResNet 50 backbone. So the reason why we used a pre-trained feature extractor for this one is because training a neural network from scratch is a very time-consuming and money-consuming operation, because it requires a very high processing GPU and hardware, enough storage, and that is a very time and money intensive. So that's one of the reasons we decided to use a pre-trained one. And the other reason we decided to use a pre-trained feature extractor is that features are generally same in throughout different images. So for example, every image is going to have some kind of edges, right? Some kind of like contrast. So feature extractor is more general to images than to specific data set. So it makes sense to use a pre-trained one due to that as well. And the last part we have for our network is called classifier. So classifier, if you can see here, classifier takes the things, the objects regions from region proposal, and then classifies it into different categories that we've sorted it as, that we've decided our network should be able to detect. For example, you can take this small green one and say, oh, that's a pelican. You can take the other one and say, oh, it's a seagull, and then so on. So for our purpose, we decided to use 3 different classes: pelicans, seagulls, and background. So even though we were just looking at the number of pelicans per image, we decided to do seagull as well because, if you look at the left-hand side here, you can see that they're pretty different, right? So it's very different. But if you look at the right-hand side, when they're flying, they look very similar. And how neural network works is that they detect different features from the objects, and then it uses that to classify it. So these two are very similar. These two have very similar pattern, color, structure. So it's going to be very confusing for our network as well. And which gives us a higher chance, like it makes the network prone to like mistakes and errors. So that was the main reason we decided to do include Siegel as a different class as well. So now I'm going to move to how we made the training data. We, for our research, we had the images collected already. So all we did was we labeled the data, and then we made it ready for our neural network to be able to read. So the two main ways we did it is we did some manual labeling. So that is, we just opened the image, picked out the pixel coordinate, and then just made some boxes around it manually, just by looking through eye and then pixels. And the next one we did was we used a software called Label IMG, where we could draw boxes, and then it gives out the coordinate itself. So the thing about like making labels or preparing data is that the labeling is a time intensive. So we could do only about 30 to 40 images per hour. And because of that, we didn't have a very big set of training data. Because of that, we didn't have a very, very big set of training data. And so what we did with the information we collected is that we put it into a CSV file because Python has a package that can read it very easily, and we can manipulate the data from there. Terry?
Terry? Seems like you might not be getting the audio.
Yeah, sorry, like there seems to be a very bad connection on my side.
Okay.
All right, let's continue. IOU standing for intersection over union is an important parameter in detecting errors that the neural network made. To calculate IOU, we obtain the coordinates from labeled images and model prediction first, and then we apply geometry knowledge to find the dimensions of the area where two overlaps and the union of both. Then we can thus calculate the value of IOU by using equation that is IOU is equal to the area of overlap divided by the area of union. Evaluating IOU is significant. First, it gives a pattern of threshold for the model prediction, since we can see how most values of IOU are distributed, and therefore to determine a good threshold. Second, with the threshold being determined, this will figure out if there are cases of true positives and false positives, and maybe other types of errors. Over the image we labeled and used to train the neural network, we need to discover a pattern between the number of pelicans in an image and the number of pelicans that have the particular number of pelicans. The histogram is demonstrated as at the top right corner. By directly observing the histogram, we can see that most images we labeled and we used contain 2 to 4 pelicans. This tells us how many pelicans there are in a certain area that we set the camera there. This also gives a visualization to assist our further statistical studies. We will run our sanity checks in 2 distribution models, Poisson distribution and chi-square distribution. Poisson distribution depicts the model in which independent events happens in a certain time interval. We believe that the appearance of one pelican is independent to the appearance of another one. Therefore, we use Poisson distribution model to sculpt the distribution of pelicans within the images we used. The histogram, as well as the probability density function of the distribution of pelicans in images, are shown at right. Under this model, we are 95% confident that if we take many pictures, the number of pelicans will fall into the range from 5.00 to 5.00. That said, the number of pelicans in an area when camera set up is most likely 4 or 5, calculated by Poisson distribution model.
Let me interrupt you there. Are you having issues with your microphone? Or am I the only one who's hearing like the
Yeah, I'm hearing that.
Okay. Could you try talking again?
Yeah, sure. Well, seems like chi-square distribution describes the pattern of distribution of the sum of squares of different independent standard normal distribution variables. We believe that distribution of Pelicans in an image is random, therefore we suit our data to the distribution model. The probability density function of the distribution of Pelicans in images are shown at right. Under this model, we are 95% confident that if we take many images, the sample mean of each will fall into the range from 3.82 to 4.17. That said, the number of Pelicans in the area when cameras set up is most likely 4.
Oh, so for the conclusion part, so our neural network had a lot of false positives. So if you can see at the picture, you can see that the first image on the left has 3 boxes, and the image on the right has 2 boxes, even though the pelicans, only some of them captured the pelicans. So we had certain reasons for getting false positive. One of them could likely be because we didn't have enough training data, and we tested it on like different. So basically our network did not get enough chance to train to get different features of pelicans, right? For improving the accuracy, we plan to do different things. So among which one of them is the first is labeling, of course, and then the other one is data augmentation. So that means we're going to take the data we already have, and then we're going to augment, change it, so like rotate it or like resize it, and then use that. And so far we have not done any batch normalization, so we're giving 1 image per batch. It turns out if you give multiple images in a batch, then it works out a little bit better when training the data. So we're going to try that, and we're going to try a little bit of image pre-processing. So maybe we're going to scale down the images a little bit and try that as well. Yeah. Thank you.
Wonderful, thank you. Yeah, thanks, clapping. All right, fantastic. I loved hearing about how to bring computer science into biology. This is really fun. Questions?
I have one. Hello. My question is, so I noticed you went over to PyTorch. Did you build off of the neural network that was used last summer, or was this a new one entirely?
We made a new one entirely, but we did use a pre-trained one, which someone had made already in PyTorch. But we did change the classifier so that basically we were fine-tuning the neural network.
Cool. Thank you.
Thank you. Good question.
That's a good question. Other questions? We have time for one more.
I have a question.
Mm-hmm. Yeah.
How were you able to train to distinguish between pelicans in flight and seagulls in flight? I mean, gulls in flight.
So for that one, how we were planning to do it is that we were collecting enough data with pelicans that were flying, and then enough data with seagulls that are flying. So even some like minor details that we cannot see as a human, humans, like neural networks are very good in identifying those differences. So with enough training data set, the hope is that it will be able to detect 2 different classes.
Yeah, so to clarify that, the network kind of is supposed to learn that implicitly through example. And so one of the things that people would like to do is sort of find out what the network learned, but we don't really teach it anything explicitly. We just give it enough examples from each class so that it can sort of learn to distinguish it on its own.